Good afternoon. Good afternoon. We'll get started. Can we get started? Okay. So we completed the prerequisite quiz, which we hope to grade and return the scores soon, hopefully within a week. And the next thing I want to touch upon before we move further is this Monte Carlo simulation for area calculation. To remind you, we wanted to calculate the area between a circle, a unit circle at the center, and the parabola y equal to x squared. Firstly, I asked you to use the code or modify the code in order to compute this area. And then in order to verify your answer, you still need to know what the actual area is, which requires numerical integration. So let's take this one step. Okay. So on a sheet of paper, I want you to build a short table. If you have the code in front of you, you're going to run it now, generate some values for the parameters that I say, and write that on your sheet, and that will be your participation score for today. So a sheet of paper, your name on it. If you want sheets, we have some extra. Or I can provide some and write on the back. On that. Yeah, you can copy it. Okay. I'll get you some sheets. Yeah,
I don't understand something. Supposed to do like
So, silence, please. Silence, please. If you want sheets, I'm circulating some. Please take and pass. Just take one and pass the rest. Does everybody have a sheet of paper? Put your name on it and let's start doing some calculation. You should have your code in front of you or your laptop in front of you to run this. You need to generate a value and enter that on the sheet of paper. Okay. So before we begin, tell me how should you set up this problem? Like what should you check for as the success criterion? You have a square. Randomly select a point, x and a y. That is the point coordinates. And what should you do next? Did you modify your code? What was the line in which you check whether it's within the circle, not only within the circle, but also within between the circle and the parabola? How do you check that? So look at your code, write that if statement on the sheet of paper, and then we'll talk. Again, it's not a test. If you just took the effort to participate, you're going to get the credit. Don't worry about being wrong. Look at your code, write down the if statement on the sheet. You need a sheet? Yeah. Yes. That's what the question is again. The question is, you need to check whether the chosen random point is inside the circle and also between the circle and the parabola. What condition will you check for? You would have modified your code. You should look at your code and write down what you had. Was there a question like this? Okay. Now tell me, how will you check if it's within the circle? Yes.
Y minus squared is greater than 1, and x squared minus y squared is less than or equal to 1.
X squared minus y squared or x squared plus y squared?
X squared plus.
You want to check whether x squared plus y squared is less than or equal to 1. That's for checking if it's within the circle. And you also want to check if y is greater than x squared. Correct? Everybody had that? Or even if you didn't, it's okay. You learn now. Okay? Yes?
What was the first term?
First term is you check within if it's within the circle. If x squared plus y squared is less than or equal to 1. That will check whether it's on or inside the circular region. And then you check whether y minus x squared is greater than or equal to 0. So you can see the highlighted portion. This is what I would add to modify my code to check whether the chosen point is in the intersection of the circle and the parabola. With me so far? You had down on your sheet. Okay, 2 more questions. Okay. Any doubts before I go on? Okay. All right. So I'm going to choose a square of side 3, and I'm going to try, let's say, 100 trials. Okay, you don't have to write anything at this point. Just look at the screen. Okay, I'm choosing length equals 3 and number of counts equal to not 100,000, 100. Okay, and I'm going to run my code. Oops. Yep. If I run my code, I'm getting an answer of 10.08. I hope this is visible. 10.08. Okay. How do I check whether this number is to be trusted? Was there a question? Can it go now? This is the formula for computing the area. Count divided by the number of trials n multiplied by L squared, the area of the square. This makes sense to everyone? Formula for area. Okay. Now you get an answer of 10.08 if you choose L equals 3 and sorry, not count. Sorry, that was a mistake. All right, not 10.08. You will get about 0.99 if you did 100 trials with a side of 3. Can you try that on your code and see if you get not exactly this, but at least something similar? Getting around 1.99, something like that. 1.08. That's close enough. Something similar. If you run your own code repeatedly, each time you'll get a different value. Like you can see 0.81, 0.90, 1.26, and so on. Every time it's all random, right? Okay, how do you trust this number? Like, is this number correct? Without knowing the true answer, how can you tell if this is sensible or not? That's the second question. What can we do to ensure or test the authenticity of this calculation? Yes. You want to make it small, right? So you don't want to choose points from a wider region. So here's what you do. Here's what you do on your sheet of paper. Okay, let's do this. Let's make a table. Okay, let's make a table. On one side, you can vary L. On one side, you can vary N. For N equals 100 and L equals 3, what was our answer? It's about 1. It's about 1. That's what we got, right? Now, what's your name? Daniel, right? Daniel wants to make the square smaller. So from 3, let's make it a factor smaller, factor of 2 smaller. Let's go for 1.5, run the code and record our response. So while you do that, I'm just going to make my table a little cleaner. Okay. All right. So I'm going to do N equals 100, L equals 3. And we got an answer. Whatever you got, you can write that down, something about the order of 1. We want to keep N constant, N equals 100, and go for L equals 1.5. What do you get from your code? about 0.6. I'm getting 0.67 here. If I keep running this, I get values that are roughly distributed from 0.6 to 1. Everybody following with me? You are getting values that are roughly distributed between 0.6 and 1. So I'm going to write. Yeah, we are just focusing on area. Don't comment out the difference area of the circle. Just get the area value. Sorry. Why is it too small, do you think?
The length of half the square at 0.75.
So the point of intersection is what? Sorry? 0.786 and minus 0.786. So you're saying if we choose 1.5, it's going within. That's a fair point. Let's not do 1.5 then. Let's do 2. Actually, let's do 1.5. Okay, let's do 1.5. It will teach you something. Stick with me for a minute. Okay. So if you do 1.5, you get between 0.6 and 1. Okay. Now let's do n equals 100 and L equals 2. Can you change this to 2 and see what you get? 1 second. So if you run this for L equals 2, you get values that are roughly distributed from 0.7 to 1.3. You get a lot of spread each time, 0.7 to 1.3. Yes, what was the question? Yes, this is the code I asked, uploaded on Canvas. I asked you to play around with, and now we are trying to use it to answer a few questions.
I'm getting the area spread because some of my values are smaller than 0.7 and some of them are larger than 1.3. So
It could be, I'm just guessing.
you can pick it up.
I just run it like 5 to 10 times and I'm eyeballing it. I don't know the answer going in. Yes. We'll have to take that separately, but what I would maybe ask you to do is look at your neighbor's monitor and answer the questions together, because it'll take some time to figure that out. We want to keep moving. Okay, maybe do this offline. Yeah. Okay. So now the question still remains, what are ideal values of N and L so that you can actually trust this calculation? When is this calculation going to converge? Should we make the square very large? Should we make the number of trials very large? What did we discuss last time? We need to keep doing more trials to get better accuracy, right? Why don't we keep L at 2 and go 10x larger in the number of trials? So from 100 trials, run it for 1,000. And what I want you to do now is run this like 5 to 10 times and see the spread of values. Previously, what was it? Now, what is it? 1,000 trials, L equals 2. The spread has gotten much narrower, right? So what is it now? It's somewhere between 0.9 and 1.1, I would say. So for N equals 100, N equals 100 and L equals 2. 1 second. It's between around 0.9 and 1.1. What was the question?
Are you considering the negative values?
Negative values of which one? Forget the difference. Okay, let me show you the code here. Just look at the calculation of the area, comment out the difference. Don't worry about the difference because this difference is based on the area of a circle. We don't know the area of this shaded region. So I don't want you to compute difference, just compute the area. Okay. So the table we are filling out here is just for the area, not the difference. David, you're still not clear. That could also be because you didn't change the criterion for success. Did you update it here? Did you? Okay. Okay, so now from about 0.7 to 1.3, the spread has now come down to between 0.9 to 1.1. Maybe you should try running 10,000 trials at the same L value. So next thing is 10,000 and L equals 2. Yes.
Almost there.
So I would run N equals 10,000 and L equals 2. Okay, I'll go back to my code. I will run 10,000 trials. If I hit run, I'm getting 1.02, 1.08, 05, 06, getting something that fluctuates between 1.02 and 1.08. You can write down whatever you get. You don't have to copy this number. Run your own code and write down what you see.
For those who, like, I've been just writing that, is that okay too? Is that acceptable as well?
That's fine, but the goal is to get you to get your hands dirty. Okay, so far, what is our trend line from keeping the size of the square constant but increasing number of trials? What are we finding? What are we finding if you just increase or do more trials? More precise. Not the keyword is it's getting precise because your estimate is now fluctuating between a narrower and narrower range. With me? This is the key point. Those who are writing, please take a moment, look up, listen. As you increase the number of trials, the range of the spread gets narrower. Let's do 100,000. Okay, let's do the next step. N equals 100,000 trials and L equals 2. You run your code and tell me what happens. I'm going to run my code for 100,000 trials and L equals 2. And my values are seen to fluctuate somewhere between 1.05 to 1.07, or maybe even around 1.05 to 1.08. What is your experience? It's thank you. It's key that you tell me what you experience, because if you are not seeing this, that means we need to change something in your code. The contradictions are important. Don't think that you should keep quiet. You should talk if something contradicts. Okay. Is everybody seeing this? It's getting narrower. The gains are when you went from 100 to 1,000, the precision increased drastically. When you went from 1,000 to 10,000, it still improved. But when you went from 10,000 to 100,000, it is improving, but it's also kind of flatlining. Do you see that? The gains are decreasing. The gains are saturating, and you can push this further and do 1,000,000 trials and see what will happen. So let's say we do 1,000,000 trials with L equals 2, and you tell me what the spread of values are. Less than 100. Okay.
106.
Okay, so I'm doing 1,000,000 trials. I'm running my code 1.0650 0672, 0665, 0668. So it's somewhere between 1.06 and 1.07. That's my experience. Are you seeing something similar? David, we okay? Thank you. So the conclusion is, at least for this part, for a given size of the square, your accuracy, your precision goes up if you do maximum number of trials that are practical. Okay. So when you ran your code like 5 to 10 times and you wrote down a spread of values, that act is called what? We talked about this. You ran it 5 to 10 times, you got some values. You could have run it like a million times, but you didn't. But you did only 5 to 10 times. What is that act called? Sampling. That is the act of sampling, taking a few values so that you can make an inference about the entire possibility. Okay. Now, what's your name? Now, Kenzie asked the question sometime back, is L equals to the correct value? Or if somebody had mistakenly used L equals 1.5, how do you kind of say that is not correct because it doesn't fully encompass the area of interest or whatever? How do you check whether a chosen L value is meaningful or meaningless? Or in other words, it encloses the entire area or not, especially if you don't know the entire area or all the intersection points mathematically. How do you check that? I'm going to rule that out. There has to be a better or not a better, but an alternate way to check something that you don't fully understand or fully know about. I gave you a curve, right? I gave you the equation for the curve and you kind of know where the intersection points are. Suppose you're not given an equation for these curves. Suppose you are just given two pictures or two curves and you randomly have to select points and see literally whether they are within or outside a region. How will you do this? Or how will you cross check your choice of L for the square? True or false question. Your choice of L will have an influence on the magnitude of the area that you are computing. True or false? The area shouldn't depend on your choices. Would you agree with me on that? Then the answer to my question is false. The L that you choose should have no bearing on the area that you compute. It's like saying the type of thermometer you pick, it decides your temperature. It's the equivalent of saying that. So if that statement is true, that is, regardless of what value of L you choose, the answer shouldn't depend on L. That's a reasonable value of L, right? So how do you go for that value of L? Or in other words, how do you come back and check whether 1.5 is too small or just enough? If 1.5 is too small and 2 is just enough, how do you prove it? I'll pose the problem this way. You get to draw a square. It's easier if you have a way of thinking about L, because this problem is easy. You can know the point of intersections and do the math. But let's say you have a really complicated area, which is it's not easy to know all the points of intersection. It's much easier to draw a square around everything or an arbitrary square and keep varying the size of the square until your answer no longer depends on the size of the square. Okay, what I'm trying to get at is this. Okay, this is the answer that you are seeking, or the area. This is the side of the square, L. If your area doesn't depend on your choice of L, how should the values be scattered. We talked about correlation coefficient, right? How should they be correlated if they don't depend on each other? Parallel, right? If your choice of L doesn't influence area, it should be correlated like this. For all the choices, the same area results. If there is a region where the area correlates with L, what does that mean? Thank you. That means in this zone, the box is too small. It is not a meaningful calculation. You need to keep pushing L beyond a region where the area no longer depends on the choice of the box. Okay, so we did this calculation with L equals 2 and we varied N. Okay, and at the end of it, what did we figure? We figure that 1,000,000 points gets you very good accuracy or very good precision. Now, what we'll do is we'll pick N equals 6 and we are going to vary L. Okay, with me? Clocked out? Checked out? No? Okay, so now I want you to continue doing this. Yes.
So if you go back to the thing we edited at the first.
One second. Yeah. Yes, please. Sorry.
No,
Yeah.
you're good. If you go back to the if statement that we edited at the beginning, and if you take out the equation of the ellipse, and
Yeah.
then you check your L values, I don't know if it matters or not, but I was looking at the outputs and the area actually dips below the area of the circle. So is that a way to check it? Because as soon as you go up to 3 for the L value, your area is same as the circle, but at 1.5 it's smaller.
I mean, you can have any statement in here. You can check for any region. Could be a intersection or it could be an ellipse or triangle or anything. What we are going to look for is non-dependence on the length or independence of the length. If you can see, okay, what is the sanctity of L equals 1.5 or 2? Why not keep it 0.5? Why not keep it 1? Right? You don't know whether 1 is enough or 0.5 is enough. So what you do is you systematically vary L from, let's say, even 0.75. We'll go L equals 1. We'll do L equals 1.5. Oops. We'll do L equals 2. We'll do L equals 4. L equals 8, and so on. Let's keep, and at the same time, we are also keeping the number of trials equal to 1,000,000. Okay. So run your code for each combination. Keep N at 1,000,000 and run L for these values and fill out the table. You'll see the trend. Yes. Sorry. This is just the circle. Okay. You need to add the condition to add one. So again, if I need to do this offline,
No, it's
okay. Okay. Or if you want, I can show you this. Okay, please run this. I want to run L equals 0.75 and 1,000,000 trials. Please run that. If I run this, I'm getting values that are something like 0.24 to 0.25. Okay, 0.24 to 0.25. If I take the same code, run it with L equals 1, I'm getting 0.41 to 0.42. Are you with me so far? Is this your experience also by running the code for L equals 0.75 and L equals 1? Yes, no?
Yeah.
See, by setting the number of points at 1 million, even if we are getting a wrong answer, we are getting a very precise answer. Did you see that? Even if 0.24 is absolutely not the value that the true answer, you're still getting a very precise answer. It's not a wide range. Okay. So the number of trials n directly correlates with the precision of your answer, and the L correlates with the accuracy of your answer, as you will see shortly. Accuracy and precision. Okay, for 1.5, what are you getting? 0.83 to 0.84. Thank you. Okay. And for L equals 2, we are getting 1.06 to 1.07 as we did before. Okay. And for L equals 4, what are we getting? L equals 4. If you want, you can include L equals 3 also. Oops. For L equals 3, I'm getting, oops, whatever. Again, 1.06 to 1.07. And for L equals 8, sorry, not 8, 4, I'm going to get 1.06 to maybe like 1.07 again. And finally, for L equals 10, I'm going to run this and see. We are getting around 1.05 to 1.08. The precision has somewhat reduced. That is, the range has expanded, but we are kind of there. You should try this and possibly fail for you to understand. With me so far? Yes. Now take a moment, stop writing, look up. As you cross over from 2, the answer stop depending on L. Do you notice that? Between 2 to 10, you are getting pretty much the same range. You will never get a single number. You will always get a range. That's fair. But at least the range doesn't depend on L anymore. So the ideal value of L, where the answer is convergent and doesn't depend on L itself, lies somewhere between 1.5 and 2. If you really want to hunt that down, what would you do? You'll try 1.75. If 1.575 looks more like 1.5 or more like 2, you'll decide whether it should fall on this side or that side. You'll try 1.95. You'll narrow the interval more and more. Eventually, you'll figure it out. Okay? Make sense? What's going on with L equals 10? The precision is dropping when you went from 4 to 10. What's going on?
Printing out your.
The scatter is increasing. Success, the number of success, right? So what would you do to counter this increase in L or increase in the sample area? Do more trials. If you have to cover a larger range, you do more trials. Maybe instead of n equals 10 power 6, we'll try 10 power 7, like doing 10 million trials. L equals 10, n equals 10 million. So if I go back to my code, change, add one more 0, I'm back to getting between 1.06 and 1.07. So now tell me, if I ask you to get me a single number as the area of that shaded region, what is your strategy? I want a single number. I don't want a range. What value of L and N would you pick? You can pick 3 or 4 or 2. Anything about 2, I think, number 1. L about 2.
Minimize the trouble so that it's not spread out.
You want to do an efficient calculation, so you want to keep L the smallest and N as large as necessary. You don't want to do like 1 trillion values unnecessary. Just want to keep it to 1 million. So let's say L equals 2 and N equals 10 power 6 is a good choice. Now I need a single number as the answer. What will you do to report to me a single number? Yes. You're going to say something? You take this combination, you run it for, let's say, 10 times or 50 times or 100 times, you're going to get 50 values of area. But I don't want to know 50 values. I need to get a summary of that. What's your strategy? You are going to give me an average and a sample standard deviation, correct? Or a sample variance. That is exactly what this chapter 6 is about. We are going to take a set of samples and get their mean and standard deviation. So in the 3 minutes we do have, you're going to modify your code to add these two formulas to your code. Or maybe if we can't do this now, do this as homework. You're going to run your code, let's say, for a certain number of samples, like 1 million samples. I want you to compute the mean and standard deviation. Sorry, sir. I back up. This is your code. This uses L equals, I'm going to say L equals 2 and 1 million samples. Okay. You run it once, that's like one sampling event, or one draw from the pack of cards. You run it once, you run it twice, you run it 10 times, you compute a sample mean. So I'm going to write here. Okay, run the code 10 times, each time with N equals 1 million and L equals 2. Compute the mean of the 10 values of area. This is what we call sample mean. Compute the standard deviation or variance, which is what we call sample variance. And the formulas to use are basically these two. We are trying to learn. Let's not let MATLAB learn. Okay. You do the calculation yourself by programming in a loop. Don't let MATLAB do the work for you. That's how they get you. That's how they get you. So they make you buy these AI products. You get addicted to AI and you never recover. You end up paying $200 a year for the rest of your life. That's the business model. You are the consumer. So don't be lazy. Do the calculation. So I want you to add 2 lines of code to the snippet that I have provided. I want you to add these two to figure out if you run this code 10 times, what's the sample mean and sample standard deviation? That's the question for next class. For today's class, don't worry about making your sheet beautiful. Just make sure your name is on it. Hand it to Jonathan on your way out. We'll meet on Thursday. Thank you. All right.